Hello and welcome back to Calculus 2, section 6.9 on exponential models. So we suffered a catastrophic failure of the stream and everything, so we are restarting. Let's see if it holds up this way. So this time around. We're talking about exponential models. I already mentioned that the exponential models are essential to pretty much any area of human endeavor. We have exponential models covering everything from history through carbon dating, through medical field to metabolize the drug, right? To engineering and physics, and then obviously we have also finances and economics related to interest rates and so on, and then environmental issues such as garbage decay, which is a huge problem, for instance, in China, also in India. And then we also have radioactive decay for all the radioactive nuclear waste, which is pretty much all over the US and everywhere else. Another part would be biology, which I forgot to mention earlier, where we talk about population of whether it's people or rabbits or bacteria cultures, whatever it is. Exponential modeling is done as well. So the heart of the exponential modeling is obviously the exponential function, and I already have that exponential function can be looked at as the growth when the k is positive, right? Kx is positive, and then when you have negative kx, you have exponential decay. Now note that negative, that means that for both of these graphs, k is positive value, and then on the second graph, the negative applied to a positive k gives you a negative number, which is decay. The y-intercept is a, which is either initial population or initial amount of garbage or initial amount of drug that is introduced. So that that a, capital A, is going to be the initial amount at t equal 0. So plenty of application. We're going to go through a few of these and then eventually go through radioactive decay as well, talk about half-life and not the video game, the concept for decay. Now, when you're looking at these mathematical formulas, the main formula, as you've seen up there, is y equal a e to the kx, but then we replace variables, right? Use the letters that are helping us connect them better to what we want to talk about. So we can talk about population at any time t as the initial population time e to the kt. So that will be population. You can have that the amount is equal to principal e to the rate times time. That's money. You can have the mass is equal to initial mass e to the kt. This would be mass decay. So this would be the garbage and radioactive decay. Half-life would be connected to this, and so on. Well, yeah, I can say I can just say k less than 0, right? But the problem will immediately give you, as you start computing, you'll see. So all of these concepts work together. So let's start with the population problem. And this is the one where we are going to apply, once we find population model, we are going to apply calculus to analyze that model and then also see what else we can get out of the model when we use calculus. So the first part of this problem, solving the problem, would be precalculus. So literal Control-C, Control-V, all right, from PreCalc. So let's talk about population of humans. and we want the model that will peek into the future. We are going to use the real data, so I will ask Google to tell me the population in what year? 1990? Okay. Well, it's 1999. It's going to be difficult to deal with the values. Well, easier calculation if it's 1990. So, population 1990. We're talking about the world population in 1990. Total population, the world in 1990 was let's go with 2 decimals, 5.28 billion. We are going to consider today's state. We are going to look at the website that is called Population Clock, which will show the situation today. So we have 7.42. And you can find all the other relevant information. So China 1.38, India 1.28, United States 0.3, right? And Indonesia, Brazil, Pakistan, Nigeria, Bangladesh, Russia, Japan. Very interesting to see Japan in top 10 with one of the small islands. But yeah, these are the population data. You can, as I said, Google population clock, and you can see the population displayed. So we are going to use this information along with our population model. K would be the rate of growth of population. I am going to set t equals 0 at 1990, which will tell me that t is equal to 27 at 2017. And the reason why I'm zeroing out is to have easier calculations. We are going to use this point in the model first. So when you have t equal to 0, then whatever the population is in that year is your initial population. So we are getting that the population is equal to 5.28 e to the kt as the first step. And now we're going to plug in 27,7.42, which is state today. And this will help us calculate k. So population is 7.42 equals to 5.28 e to the k times 27. So now we are going to divide. By the way, you will need abacus for these problems because calculations are not going to be pretty. So when we divide 5.28 into 7.42, we have 1.41, keep 2 decimals, equal to e to the 27k. We are going to ln both sides. It's not times ln. You are applying ln as a function composition on both sides. On the left-hand side, we are going to do the ln of 1.41 and get 0.3436. When you are working with exponentials and ln's, make sure you're using at least 4 non-zero decimals, so 4 significant figures, so we are reducing the error. On the other side, you have 27k, from where k is equal to this number divided by 27, 0.01273. So we have k. So now population model is p of any time t is our good old 5.28 e to the 0.01273 t. This is the population model which we obtained by picking a random point, right, which was 1990. We also need to know that the time is counted as t equals 0 at 1990. So can you use this model to see what happened in 1980? Sure, but your t needs to be -10, right, because you're going backwards in time. If you want to check what's going to happen in 2030, what would you do? T equals 40. Very good. So 2030 minus 1990 is 40, so t is 40. So you have to just make sure that you are using correct values. So we are not plugging in the year that we want, we are plugging in the difference between the year we want and 1990. Yes? That's the population, because we have, this is P, right? That's the point, P comma P. So plug P, and then you can calculate K. So now that we have this population model, I would like to see whether it's good, and also what else I can get other than computing particular populations at times. The first concept in calculus we learn is limits. And I would like to see if this model is good on the long term. I'm going to let the time go to infinity and see how well this model does. Limit t goes to infinity of 5.28 e to the 0.01273 t is equal to infinity. This calculation immediately tells us that this particular population model is garbage for the long run, because we know that we cannot have infinite population of humans on the planet, because we don't have infinite resources, we don't have infinite surface area to fit infinite amount of people. There is a concept that it's calculated called carrying capacity of the planet, which tells us approximate amount of population that planet can sustain in terms of food sources, energy resources, space for housing, and so on. And depending on the study, it's anywhere from 12 billion to 15.2 billion, I believe was the largest one I saw. So when you consider that carrying capacity, then you consider the explosion of population that we have. You can see that in 1990, right, there was 5.28 billion And then in 2017, only 27 years later, we have 2 billion extra, right? So the population is growing very quickly. Now you might be interested in at what year we might reach that critical number of, let's say 15.2, but it could be 12.7 billion. Again, depending on a study for carrying capacity of the planet. The carrying capacity is computed by simply looking at the growth of each nation, taking the average, and then right, which is all the contributions of food and energy and so on, taking the average and then projecting what, in terms of population, the planet can sustain. The reasons why these numbers are so wildly different is because, obviously, different averages depend on how you average population. So we can calculate using this model. So we see that this model is not good for long run. We also know that from the graph, because exponential function rises quickly. But then our population actually is rising fairly quickly as well. So if you are looking at the population, you can predict to some degree of certainty how far down the line we have to wait to, let's say, reach, let's go with 13 billion. So when do we hit 13 billion mark? How about that? Well, clearly the question is, for what time we are going to have 13 billion? Well, we have our population model. Your target population is 13, and the rest of the model is as is. And you will be able to compute t. Again, divide 5.28 into 13. So 13 divided by 5.28 is 2.4621. And then ln both sides. There's a 3 that I missed. There we go. We ln both sides. So now we have ln of 2.4621, which is going to give us 0.90101. So just 1 equal to 0.01273 t. Divide this by 0.01273 to obtain 70. 70.8. So that will be about 71 years. Again, these are all rough estimates. You're not going to go and say 70 years and 10 months, right? Because this is all estimate. About 71 years. So what year should reach this 13 billion mark looking at our model? It's going to be, yes. So it's going to be 1990 plus 71 is 2061. So we are expecting, if the population grows the way it is using the this exponential model, we are expecting to reach 13 billion, right, which might be carrying capacity by looking at some studies in 2061, which is less than 50 years from today. What happened? Yeah. What other concepts from calculus can we unleash upon this model? Well, definitely derivatives. If you think about the derivative is calculating the rate of change. I can calculate the rate of change of population in any year I want because now I have the model. Again, limit told us that this model is garbage on the long run. So we are not going to go far from where we are right now. You know, push 10, 20, 30 years ahead. Okay, the model should be, reasonably good. But don't go far. I can compute the rate of change of population in, let's say, well, we can do it for this year. We can do it for, let's do it for 2020. So what is the rate of change of population in 2020? Well, first what you should do is 2020 converted to our t is 30. You have to have that. Also, since we are talking about the rate of change, we need to take the derivative of our population model. Population model P of t was P0, which is 5.28, e to the 0.01273 t, if I remember well. 528, yes. So we are going to take the derivative. Now, taking the derivative of exponential function, you will just multiply these two numbers. So dp dt, which is the change of population in time, the derivative, is going to be these two numbers multiplied. So let's see. 5.28 times 0.01273 to give me 0.0672 1 e to the 0.01273 t. And now we are going to plug 30 into t, and we're going to have this this problem. So I'm going to say times e raised to the 0.01273 times 30, and then close parenthesis. I'm doing all of this in one shot. So dp dt is equal to 0.098. Now this is billion. 0.098 billion. So we are looking almost at 100 million, right? So what this number is, sorry, this is not billion, this is billion per year in 2020. That's what it means. Because you can see that it's dp, it's population over time. The units must be number of units, in this case people, divided by for 1 year, right? So in 1 year, and this is calculated for 2020. If you change that 30 to any other number, clearly you are getting a different number. You're not getting 0.098. You will get something else for that particular year. Yeah.
That's how many people we gained in that.
Yes, very good. This is how many people we gain in that year. So this result here means we add about 100 mil in 2020. That's what it means. You see how important calculus and derivatives are for this type of analysis. Now, again, go to biology, observe coral reefs, observe rabbits, observe wolves, observe bald eagle. They still exist? Yeah, right? Yeah. Whatever else, you can use the derivative. When you observe that population, you count how many units of species, right, you can find and tag, and then you have model. You take the derivative, right, and then you start figuring out if that derivative is going to add positive or negative number, depending on how these things go. Observe that if the species is dying out, this number will be negative. And when you multiply these two in a derivative, that number becomes negative. And then this number will be negative. It shows the rate of decrease of that population. So you can predict how many, right, of that species will die as you go on. So some countries, I believe Germany, have negative, and Japan as well. They have negative growth in this per year, right? Because they have more deaths than birth. Yes?
It's actually positive in Germany, but still negative in Japan.
Oh, I know it was negative in Germany at some point recently.
Like a couple years ago, I think.
Yeah.
It's positive now because now all the refugees coming in and actually staying there permanently.
Yeah, but it's still not birth.
Well, yeah, it's a population tracking.
Yeah. So, what else can we do? Well, we can do integral, right? And integral calculates accumulation. So I can calculate the amount of people added over a period of time from, say, 2020 to 2030. The limits on the integral will be, right, what did I say? So 30 to 40. And you integrate and you compute. You see? So we can do all of these calculations. So those are the three concepts in calculus that you can attach to these. Now it doesn't matter whether you're talking about introducing drug to a system, whether you're talking about garbage decay, whether you're talking about money accumulating in the account over time. It is the same exponential function which has variables written as m rather than p, but it's the same concept, and the same limits can be applied. For decay, we would say that in the, well, we'll get there, so I don't want to jump. So I'll stop there and move to the next. So calculate total amount of population from 2020 to 2030, and it's going to be integral 5.28 e to the 0.01273 t dt, and 20, so it's 30 to 40 equals to ... a number. So you get the idea. So addition is summation over period of time. Derivative is a snapshot in time. So we just take a look at these continuous years, right, of people existing, and then there is a snapshot at 2020. We added 100 million, right? There's a snapshot in 2021. We added another 100 million, right? Snapshot in 2022, right? And so on. So the snapshot, so derivative is the snapshot. The integral is the summation over the period of time. And the limit, generally, you let the model run to infinity and see if it's viable on the long run. To give you another engineering idea for this, say you are Sony or Samsung creating a battery, right? And you have the exponential function model that will charge that battery. Now, battery is energy storage. It's taking electrical energy, converting it into chemical energy. It stores energy as chemical energy, and then when you want to retrieve that, the conversion is done back. Chemical energy is converted back into electrical energy, and then when it's depleted, you recharge it and go back and forth. It's all good and right, fine, until you figure out that you missed something somewhere. You didn't check with the limit, and your buildup of the energy is infinite. And what is that? Exactly, right. So the idea is to actually apply these concepts as you are designing things to make sure that, you know, the bridge and building that you design is standing and that the batteries are not exploding and things like that. We can talk about the money, and I like this particular problem because we have the compounding formula which will tell us exactly what our payment is for the car that we desire. But then we realize that that formula in the limit is actually, because we learned last section, right? In the limit is just this exponential formula, which means that this calculates the absolute maximum that you would be paying. So say that you want to get a car at, what's the price tag? 20K is good? Sorry, for 20,000 at what interest? Interest is how much? For a car? That's crazy. 4% still high, but I was about to say 2.4 or something like that. Huh? 20K. Interest rate? Out. That means you have no credit. 14%? I've never heard of that. The most I heard was 11. Okay. Yeah. Do you find this 7s and 14s? Yeah, let's just go with 4. Let's not make it grim. And how many years? 5 years? Yeah, I know they go now for 7 years, with the lifetime. Maybe you can swap a kid or something. I don't know. So how about 5 years? So I'm just going to label this exact, but we are not going to worry about the exact. The amount you owe is the principal times 1 plus rate over the compound, which is the 12 in this case, times NT, which will be 20K 1 plus 0.04 divided by 12 times 12 times 5 is 60. This is the exact amount you owe after everything is computed. And let me just get the app because it's easier. So 20K times 1 plus 0.04 divided by 12 raised to 60. So the amount you owe after interest rate is applied is 24,419 and 93 cents. I am going to divide this with 60 to get the monthly payment of 406.99, so 407. Okay, 406.99, and then next decimal is 8, so that rounds it up, so 407. So I want to say exact, but this is not exact because I did not calculate in the tax, which is on 20,000, right? That's 1,400 plus all of the fees that you have, the title, the registration, the insurance, right, and all of these kind of things, they add up to some amount. So the amount that if you don't have a down payment, this amount would not be 20K, it will be maybe 22, 23K to start off, which brings this up, brings that up. But let's ignore, let's say we live in a world, it's vacuum, okay? So yeah, what happened? So guys, this is the calculation. It's not exact, obviously, because I ignore the tax and everything else. But what we learned earlier is that the limit as n goes to infinity of 1 plus 1 over n to the n is equal to e. That means that the limit n goes to infinity of 1 plus r over n to the nt is going to be e to the rt. Now, once you have this limit, and you can prove this limit using L'Hopital's rule in chapter 4, takes about 2 minutes, you realize that this formula can be written as the continuous compounding as principal e rt. And in our case, there will be 20k e to the 0.04 times 5 years. And if you run this calculation, you get 24428 and 6 cents divided by 60 for monthly payment, and then you get 407 and 13 cents. What this gives you guys is the ceiling. At this interest rate for 5 years, there is no way in hell, that the payment is going to go over 407.13. Now look, we struggled with the complicated formula, right, to remember and compute, lots of order of operations and everything to get 407, and then we use this formula here to get 407.13, which gives you the max payment. If this works in your budget, then this works as well, right? So you can calculate the cap on that car, right? Now talk about student loan, talk about other types of loans that you might want to take at some percent. They all work the same way. Mortgage doesn't work the same way. You have to be careful about mortgage, but certain types of investments, savings accounts, and then car purchase, maybe you borrow $2,000 or something to buy the computer and stuff. They work this way, and you can work out yourself these payments before. All right. All right. The next part of the lecture is one of my favorites. We're going to talk about radioactive decay. We're going to talk about, first, we're going to define the concept of half-life. So half-life is the time it takes for a sample to decay to half of its original mass. So half-life is a time in which a sample of something, whether it's a piece of garbage, banana peel, or uranium sample that radiates, right? So it's time in which that sample will lose half of its mass. If you start with 10 grams, you wait, it's going to be 5 grams eventually, right? Then half of those 5 grams, you have to wait another period of time, and so on. For certain biological waste, like banana peel, for instance, you don't have to wait for years for banana peel to disintegrate, right? So it will be at 10 grams and then 5 grams within a few days, and then you wait the same amount of time to go to 2.5 grams, and then again same amount of time to go to 1 point. So the half-life will always half the half, okay? You have the entire mass of 10, you wait, let's say 5 days, it cuts it in 5. You wait another 5 days, it cuts it in 2.5. You wait another 5 days, it cuts it in 1.25, and so on. So you have to wait the entire half-life in order for it to lose a certain amount. Now you have radioactive elements like uranium, plutonium, and so on, where you have to wait thousands of years for it to decay to half of its mass. So technically, considering environmental problems, whether we're talking about radioactive decay for nuclear waste, or if we are talking about the decay of garbage, which is plastic, or then you talk about decay of organic food in a compost and so on, it's the same equation that governs all of those. It is going to be a loss of mass. We call those decay problems. We are expecting K to be negative number when we do calculation. Now, my favorite problem is the toothpaste problem. So the good old times in 1940s, the first teeth whitening paste called Doramad was released to the market. This is the Doramad paste. There it is. See? And Doramad was used to whiten teeth, right? We have those. We have the toothpaste today as well, but it works a little bit different. You see, the way they figured out at that time was, oh, look at this. This is called the isotope of thorium, 229, and it really bleaches the teeth white, right? So let's brush, 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 and then people started dying because you take all of these radioactive isotopes, you keep brushing with them to make your teeth white. So if you look at this, right, then it was, okay, reverse, reverse, back pedal, right? Back pedal, don't buy Doramad. Apparently it's not good. So people didn't know a lot about radioactive materials and so on, because those had been found and researched in the beginning of the 20th century. We are talking 1913, 1915, major papers written on radioactive elements, right? And people didn't know the dangers of, prolonged exposure to radioactive elements. We are all constantly exposed to radiation, but our skin evolved in such a way to protect us from the natural occurrence of those elements. The problem is that when we gather a lot of that material on a pile, like for nuclear fuel or nuclear waste, or to make a bomb or whatever, or when we drop a bomb, right? Concentrated, or when the nuclear plant goes kaboom, concentrated radiation is something that we can't handle because we are not at that step to handle that much radiation. So Doramed was a toothpaste that did an amazing job in whitening teeth, but then killing everyone shortly after. So what we're going to do is we're going to run this calculation with half-life and see. So thorium-229 has a half-life, that's the, oops, you can't see it. So it has a half-life of 7,340 years. So this means that you have, if you have 10 grams of thorium, right? You have 10 grams of thorium. It will take 7,340 years for it to decay through radiation to decay down to 5. Then you have thorium. Yeah, yeah, like uranium, plutonium, right? It's a radioactive element. So you can look up that stuff online if you're interested in these kind of things. So now what do I want to know? Well, first of all, we have the model. The mass is equal to initial mass e to the kt, and we are expecting this k to be negative because, right, life. It's decay model, so it's negative, right? That's why I say life. Now, how do we calculate k? Observe that we have half-life, and the half-life says that in this many years, so that's the t, the mass is half of original mass. So that's what the essentially what it says. Half-life is the time in which original mass, whatever amount of grams you have, is going to be cut in half. So now when you plug in, you get that the mass is half of the original mass equals to original mass e to the k times 7340. So all I did is I plug in all of the values that I have. And now observe that this m cancels. It doesn't matter whether you have 3 grams or 3 tons of thorium, right? It's a loss of half of it. Half of it will be gone, whatever you start with, and you see it's not important what we have there. So that gives us the equation 1/2 is equal to e to the 7,340 k, and we hit both sides by ln to get to this k. Well, on the left-hand side, ln of 1/2 is negative 0.6931, and on the right-hand side you have 7340k. Again, ln and e cancel, and then you divide this number by 7340 to get k equals negative 0.123409443, which gives us the model for thorium. Model for decay of thorium-229. The mass of thorium at any time is the initial mass e to the negative 0.000094443 t. That's the model. With this model, I can compute anything I want. I can compute the amount of thorium that's left after a certain time as a percent. I can compute the derivative, I can find the integral, and I can also see in the limit that I have to wait how long for all of the thorium to be gone. What's the limit? Infinity. You see, when t goes to infinity, remember that exponential decay is asymptotic to x-axis, right? T-axis. You have to wait infinity of time for all of it to go away. Oh, by the way, the drugs in the system work the same way. You still have everything you ever took. It's still in your bloodstream. 3 molecules of it, fine, but 3, they're still there. Because it is, yeah. Yes?
Wouldn't it eventually be reduced to 1 and then that would decay? Over some insanely long period of time?
Yeah, but you have to understand the amount of the sheer numbers of what you're dealing with. These are the billions and billions and billions and billions of those molecules. Right? It's 10 to the 23 Avogadro's number, right? 10 to the 23. You know how much that is? We say, oh, this guy's a millionaire. That's 10 to the 6. It's nothing. Nothing. You know what a 10 to the 23 is? It's a million, right? The whole string like that. So yeah. You're right, but you'll be long gone by the time that 1 molecule decays. All right. So yes, it's quantized, but still. You know what I want to know? I want to know the percent of thorium, right? All of the people that use it are dead. It's 1940s. So let's say that everyone died by 1947. And today is 2017. Find percent of thorium remaining. Because decay is going to happen, right? Decay is going to happen. So what do? Well, time is clearly what? 70 years. And we are looking for the percent of the thorium remaining, which means that we're going to have that labeled as P times original mass, right? Because it's the percent of original mass. So this over here is the percent of original mass. And original mass, well, we don't care, because we're going to find the percent left after 70 years of decay. So plug everything in. We have percent times the original mass is equal to the original mass e to the negative 0.000094443 times 70. You see that these m's die, right? It doesn't matter if someone was brushing 2 times or 3 times or 7 times a day. That all canceled. And we have e to the negative 0.123494443 times 70. And I have that P is equal to 0.993. That is 99.3% remaining. After 70 years, they only lost 0.7 of that thorium. Conclusion? The most beautiful corpses ever, right? Yeah, the whitest teeth. I guess. I don't know. we don't know what's going to kill us eventually, right? It's going to be fun, you know, see maybe 500 years down the line, surviving humans say, hey, they used to drink milk. That's why they died when they're 90. Like, we don't drink milk. We're 700 years. Yeah, because milk comes from a cow. It's not the same species. And then they went even worse. They say almond milk. Almond, really? Milk? It's not even an animal. Almond is not an animal. But anyway, that's how silly we are. So you apply the same process to decay of carbon C14 to work on carbon decay and find how old either a piece of scripture that you dug up somewhere is, because that was written on a papyrus or some type of a paper that was actually made from a plant. Or maybe you found the painting. The recent one was when they found one of the paintings, they believe it was Michelangelo's painting. So what they did is they did carbon dating and on the paint, because all of the paint was made from flowers. If you have organic material, you can find the amount of carbon that remains, which carbon C14 decays over time. We have the half-life for that documented. And you run carbon dating, which is the same calculation we just did for thorium. You will use the half-life to figure out K, and then you will plug in to find the percent, right? The percent is, it would say 70% left or whatever, and you can calculate the T. So all of these problems readily calculate. You can go and at one point in time, I had one of the project problems was for you to go and research the Chernobyl, right? In Pripyat, the radiation levels, and to go and calculate radiation levels and see, you know, the decay of radiation and when would those radiation levels go down enough for people to go back and live in that area. It was very difficult actually to dig up anything on the recent Japan issues that they have, because I don't put the stuff up, just stuff in the sea. Nothing to worry about. And so, yes?
There's like a lady that never evacuated it for some reason. She's fine.
Yeah, well, depends on, you know, where the pockets of radiation are. It's not that everything in. It's easier to evacuate and just close off the entire area than to go and say, okay, so this block over here. Because when something like that happens, again, the wind will take the particles, right, and settle them on one building, but not on the next one, right? And then that building would be radioactive because the wind will take particles. So you have pockets. People go there regularly. Tourists go there regularly. You can go and, you know, walk around with the Geiger counter and figure out where the pockets are. And, you know, these routes are worked out very well. To observe, especially to observe, a lot of scientists will go because they have now this oasis without people to see how much planet would actually flourish if we are not around. You know, radiation aside, all the mutation and cancer and everything else aside, with the animal population increasing in plant life and everything else is astonishing to see. So all of these things. So at one point I had that on the project. So that, I mean, I could probably include it. You would work out these types, and then again, you have the model. You take the limit. It will take infinite amount of time for all the radiation to go away. Let's see how much radiation, right, units we are losing in 2020 or 2030 or 2050. So you can compute those kind of things with the derivative, and then total amount of accumulated radiation that someone will accumulate in the body that lives right there, like that old lady. You would use the integral and so on. I'm sorry?
Like the chemicals in.
Well, I At one time, I did the, but this was done in the Precalculus class, this expo marker, right? You research what type of plastic is used, and then there is a half-life for that. You can talk about the half-life of those short-life plastic bags. You can talk about half-life of banana peel, or all of those things are known, and you can actually work out a paper around that and say that, you know, it will take about 30,000 years for this to go to half of its size. Now, obviously, it will not decay to half. It will, you know, it will lose mass across, and that's alpha radiation. So everything decays with alpha radiation, constantly, including us and the marker and the computer, everything. Oh yeah, even worse. Yeah, I was gonna skip the comment, but I had a really poisonous one this time. So the internal censorship kicks in, like when it's really bad, like that. It's just, you know, I have to stop, and I have to say there's something terrible that I was supposed to say, and then I managed not to. So you're welcome.
Yeah, but you should say it anyway.
Yeah. So scary. What else? So technically, I mean, that's it. If you look at the homework, it's going to be all about this type of decay. They give you different, obviously each element has its own decay rates. So C14 carbon for carbon dating, uranium, plutonium, all of these that we use in our power factories and so on. So there's a lot of different stuff that you guys can research. So that's it for this lecture. Again, your book doesn't include a lot of calculus analysis with limits, derivatives, and integrals. I am attaching that to this lecture at the end of every problem because calculus analysis is important. And now we're going to talk about the exam. All right, so let's shut this. Yeah, exam is coming up. Maybe, I don't know.